Okay, we're going to do one last example of a boundary value problem in cylindrical coordinates. And we've already seen the Bessel equation and the modified Bessel equation crop up in previous examples of cylindrical coordinates. But in those examples, all it ever did was allowed us to reject potential eigenvalues. We never accepted the solution to a modified Bessel equation. I'm really talking about the modified Bessel equation. So now we're going to get to an example where that's not the case, where we'll use the modified Bessel function. And what we're going to do, it's a problem similar to this one that we already did. It's another steady state temperature in a heated cylinder, but we're going to have different boundary conditions this time. It's going to be held at 0 at the bottom and the top, and the outside sides are going to be a function of the height, c. So let's see what happens there. By way of review on this problem, I kind of went through why we picked minus lambda here. We could have picked plus lambda. Turned out nicer when we picked minus lambda. It was a nicer case for the R equation because we could get eigenvalues out of the R equation. Let's go to this last little example. Here it's the same partial differential equation governing the temperature, but here are the different boundary conditions. Here the cylinder only has a height of 1, temperature 0 at the top and bottom, which equals 0 and c equals 1. Here's the function of c it is along the sides, outside. I could split it up the same way I did before by separation of variables product method. And depending on how I pick the sign of lambda, I could either have these two differential equations or these two different equations. Let's look at the boundary conditions. Let's look at these two guys. Use the product method on the boundary conditions as well, which leads us to these boundary conditions on the z equation. And look, if we choose this one, we have a complete, we can get the eigenvalues from the z equation. So we're going to pick this sign convention on lambda to give us these two ordinary differential equations. And then this on the z equation, it's this familiar case where we already know we can reject non-positive eigenvalues. So we pick the positive eigenvalues as the z equation is of this form. The argument of 0 for z says z is just a and s equals 0. So we're left with this surviving function. And if we put in 1 for z, we get this equals 0, which leads to the eigenvalues. The eigenvalues are going to be pi squared. These are the eigenfunctions. These are the alpha sub n. So now we have what our equation is. Use the same eigenvalues. And this is a modified Bessel equation, which has this general solution. Modified Bessel functions of the first and second kind. But we need to keep it bounded. Functions of the second kind are unbounded at the center of the sphere where r is 0. So here is our surviving function, the r equation. So we have r solution and the z solution. We put them together into the u's. Here's our u. Sum it up over all the u sub n's. And here is our solution that satisfies everything but that outer boundary condition. See, here we kept Modified Bessel functions of the second kind. Didn't reject them this time. Used them. So here's our solution so far at the boundary condition where r equals 1. That's the outer surface. Plug in r for 1, you get this, and that equals the given function. Well, look, we just need to expand it. We don't need any Bessel. What kind of Fourier series do we need? Not a Bessel series, not a Fourier Bessel series. And that's this form, and that's just a good old sine series like we did a long time ago. So we'll expand this function in Z using the sine series, Fourier sine series. To get it to match, P equals 1. You do have to take this integral. I'm not going to go through that. It's kind of tedious, but it has a very simple answer, 2 over n pi. So we match coefficients, and it says a sub n I sub 0 equals 2 over n pi. So we now have the a sub n's. They are these guys. So everything's so simple now, we can put it together in all one summation. Pull out the things that don't depend on n outside. Finally, fairly simple solution. And that's the last partial differential equation, boundary value problem in cylindrical coordinates. We'll do spherical coordinates.